Okay, hello everyone. So in this video we're going to be talking about the class of exact differential equations, and the reason why we isolate this class of differential equations is really just because we have a systematic method for solving such equations. So just for the same reason we have isolated the class of separable and first order linear differential equations, just because we have methods for solving those kinds of equations. We do the same thing with exact differential equations, just because we have a method for solving these kinds of equations. Okay, so before we get to a definition of exact differential equation, we need to just recall the following two concepts, or maybe just two variations on the same concept, and that is the concept of a partial derivative of a function f of two variables. Okay, so they have these following definitions here. So that this is called the partial derivative of f with respect to x, and there's two notations for this. This here, by the way, is pronounced da f da x, and this one da f da y. And what are these? What are these derivatives, and how does one calculate them? Well, formally, it's given by this formula here, which you see looks very close to the single variable definition of derivative. And the reason for this is because because of how we're treating y in these kinds of derivatives. So in the partial derivative with respect to x, we're treating y really as a constant. So differentiating really as normal with respect to x, and just fixing y as a constant. So treating it just as you would any other constant. And likewise, of course, the same thing for the partial derivative of f with respect to y. You compute the derivative by just treating x as a constant, and y is the variable which you're differentiating with respect to. Okay, so we have, maybe just to give an example of this, we have these two examples here. So if I give you these two functions, this is this very simple function here, fx squared y, and we want to compute the partial derivative of f with respect to x. Then, just as I said, we treat y as a constant and x as just a variable, and then differentiate as you would any function of a single variable x. And so that's why you get this 2xy here, because y is treated as a constant. Then, on the other hand, if we compute the partial derivative of f with respect to y here, this would treat x as a constant. And now here's maybe something interesting. But if x is a constant, then of course x squared is also a constant. So that this is really just a constant times y. So when we compute the derivative with respect to y, it's just going to give us that constant x squared. Okay, good. And then just to give you another example here, we can consider this f here. So sine x plus sine xy. And computing its derivative with respect to x, its partial derivative with respect to x, we just get that, okay, we're going to differentiate the sine x as usual, just get the cos x. And then differentiating sine xy with respect to x we're going to apply the chain rule now, because again, y is treated as a constant. So when we differentiate the sine xy, the constant pops out, and we differentiate the function as usual. And that's how we get this y cos xy. Okay, and then lastly, to compute the partial derivative with respect to y, we treat x as a constant and differentiate with respect to y as usual. And now the interesting thing here is that if x is a constant, then sine x, of course, is also a constant. And so differentiating a constant, we just get 0. That's why there's no sign appearing here, or sign of x. And then differentiating this function here with respect to y, the x is treated as a constant, so it pops out, and then we, for the same reason we got y cos xy here, we get x cos xy here. Okay, so this is just a quick brief reminder of partial derivatives, and this will allow us to define the main concept that we'll be dealing with, which is the concept of an exact differential equation. But before doing that, we need to just talk about the differential of a function. So given a two-variable function f of xy, we define its differential, df, to be an expression. It's a linear combination where we take the partial derivative of f with respect to x and multiply that by dx, and we add that to the partial derivative of y and multiply that by dy. Here, you may be asking, what are these dx and dy? And of course, that's a very good question. And the only way to answer that is, of course, a very long formal story. But for our purposes, these are just really treated as symbols, which we can manipulate as we would numbers. Okay, so non-zero numbers. Just treat dx and dy as non-zero numbers, and then whenever you have a dy over dx, that's then the derivative. That's how we think about these dy and dx's. Okay, so just as we saw partial derivative examples, here's an example of a differential. If f is given by x squared y, then its differential, as we said, is calculated. We take the partial derivative here with respect to x, and we multiply that by dx. And here we take the partial derivative of f with respect to y, and we get multiply that by dy, and then these two expressions added to each other give us the differential of the function f. Okay, so now we can get to the main concept, which is that of a exact differential equation. So if we are given any equation of this form here, so any equation of this kind, we have a two-variable function times dx multiplied by a two-variable function, a two-variable function mxy times dx plus two-variable function nxy times dy, all of that equal to 0. This again can be interpreted as a differential equation. Why? Because if we divide through by dx here, then we're going to have some function involving a variable x and its derivatives equal to 0, which is a differential equation. And then for this reason, we are interested in trying to solve such equations. So we're interested in being able to solve such differential equations whenever we get them. So we define this equation to be exact if the left-hand side is the differential of a two-variable function. That's the way to think about this concept of exactness. If given such an equation here, if this portion of the equation is the differential of some function f df, if it's the differential df of some function f of xy, then we call the entire equation an exact equation. And when it is exact, that means there is such a function f. We don't know which one. There can be many, of course. It can be different f's whose differential is given by this. For instance, up here, we know that the differential is f. But of course, if I added a constant to 1, then it would have the same differential, but f, of course, would be different. Okay, so just to say it one last time, this whole equation here is called exact if this portion of it, the left-hand side portion of it, is the differential of some function f. When that's the case, then the solution to the differential equation, to the exact differential equation, is given here. This is how we write the solution to an exact differential equation. So solving an exact differential equation is finding this function f somehow, and then setting that function equal to a constant. And then that is the solution of the exact differential equation. All right, so that's the theory now. So just to explain this just one last time here. So we have given this definition of an exact differential equation, and provided we can find, so we're given such an equation here, m dx plus n dy equal to 0. We say that it's exact if we can find some function such that this is true. Now, by the way, what does this mean? It means the same thing as just saying that the partial derivative of f with respect to x is equal to m, and the partial derivative of f with respect to y is equal to n. That's it's really just saying the exact same thing. Okay. So keep this in your mind because we'll use it in a moment. Okay, so when we can find such a function, then the solution to the differential equation is presented in this way here. So, for example, imagine we're given a question which asks us, well, a differential equation. We are to solve the differential equation given here. So we are to solve this one, which is to say we need to find this. We need to find a function f whose differential is given by this left-hand side, and then set that function equal to 0. Well, we've actually already done this, because you'll see that this here is exactly equal to this here, and the differential, this is exactly the differential of this function. So that means that this equation is exact, with f, the function, making it exact, and so the solution to that differential equation is just this. Okay, but you see, how the real question is here how to find this f. What if we know that the function is exact? How can we find the f is the real question here. So this leads us to the main theorem about exact differential equations, and the main takeaway from this video. And that's the main theorem about differential equations, and that is that given such an equation, a general equation like this one here, we can say when it is exact without knowing what the f is. And the way that we can do that is by taking the partial derivative of m here with respect to y, and checking, is it the same as the partial derivative of n with respect to x? And if it's the case, then it's exact. If it's not, then it's not exact. And that's it. So let's apply this theorem to solving this equation over here. Let's see if we can solve the following d. So first we need to check, is it exact? So let's isolate what is the n and what is the m in our equations. So this will be m, and this is going to be n. And so this is now of the form m dx plus n dy. And so let's check, can we use our theorem to see that this is going to be an exact equation? Well, let's compute. If I take the m dy, take the partial derivative of m with respect to y, then what am I doing? I'm treating x as a constant, differentiating with respect to y. So the 3 here comes down, multiplies by the 2, and I get 6xy squared. And also, if I take the partial derivative of n with respect to x, then I differentiate the x and keeping y as a constant. And then the 2 comes down, multiplies by the 3, and I get 6xy squared. And because these are equal, we can say the equation is exact. So, by the theorem, the dE is exact. So what does that mean? It means, by definition, there is a function f of 2 variables such that 2 things happen. Namely, its differential is given by this left-hand side of this equation over here, right? That's what it means. And in particular, that means that if I take the partial derivative of f with respect to x, I just get m, which in this case is 2xy cubed. So I get 2xy cubed here. And then also, if I take the partial derivative of f with respect to y, I get exactly 3x squared y. That is just by definition of exactness. Now, the question here is, how can we use these 2 pieces of information to be able to solve this equation? And that's what we'll do next. So using this portion here, let's try to understand it. We have this 2 variable function f, which we know that when we partially differentiate it with respect to x, we get this expression. So that means that using this, using exactly that, f can be written as the integral of this partial derivative with respect to a variable x. Just integrating it as usual, treating y as a constant. And this is really the main technique here. So we have to integrate this expression here, treating y as a constant. So that means that we integrate this expression, just treating y as a constant. And so this becomes exactly just x squared times y cubed. And now here comes the very, very important part, the most important part. If y is a constant, then the arbitrary constant of integration here will just be given by some arbitrary function g of y. Okay. Great. So we know that f is of this form. But now the question is, what is the g of y? We haven't really solved the problem because this g of y is some unknown function. But we can figure it out, because if we used this portion here to get to this part. But now we can use this portion here to solve for this, this g of y. And let's see how. If I take the df dx, I know that this should be directly equal to n. It's given here, right? So it should be, it is just by the blue star, directly equal to this, okay? This is just verbatim exactly the blue star. Okay, but this means something. Sorry, and I said dx, I meant dy. This means something, that if I differentiate, so f also has this form. Now if I differentiate this function with respect to y, I should get the same thing, right? So differentiating this with respect to y, we're going to get this. So let's do that. And then we're going to get 3x squared y squared. That's differentiating this term. And then we're going to get plus g prime of y, because of course we're differentiating with respect to y now. And this should be equal to whatever's on the right-hand side of this equality, and that's exactly just 3x squared y squared. Okay, this is very nice because everything works out, and we get, we just get g of y equal, g prime of y, sorry, equal to 0, because these two things cancel out. And so that means we can take g of y just equal to 0. And so finally, let me just make some space. So finally, we can write the whole solution of the differential equation, because now we know what g of y is. We can say that f is definitely equal to x squared y cubed. By the way, just one second, one thing here. The way we go from here to here is just by standard integration. So you're probably asking, why isn't there a constant here? The answer is because we can choose g to be anything. Remember, when we're solving a differential equation, we're not looking for all functions f, we're looking for a single function f whose differential is satisfying this here. Sorry, not satisfying that there. Satisfying this, these two things here. Okay, so this is our function f, and so this means that the solution then, the final solution, is just going to be x squared y cubed equal to a constant. Okay, so that was a long and thorough example, but maybe let's just do one more. So let's consider this dE here, a little bit more complicated. So again, here we have a differential equation of this kind, and we're trying to check, is it going to be an exact equation? So we look at this portion here, and we see we can label this m, and we label this portion n. And now we can use our test for exactness. So we check, is df dx equal to, sorry, df, not df, dm dy. Let's calculate what this is. So differentiating here with respect to y will just give us cos of x plus 2x e to the y. Okay, and then also differentiating with respect to x, differentiating n with respect to x, we're just going to get here the same thing. Cos of x plus 2x e to the y. And of course, these two things are equal. So this just means that the dE is exact. And so the meaning of exactness is that, so from exactness, we know that there is a function, two variables, such that its differential is equal to the left-hand side of the dE, which is to say that if I take partial derivative of f with respect to x, I'm going to get m, and partial derivative of f with respect to y, I get n. Okay, so this function exists, and now we're trying to calculate what it is. Okay, so we know that df dx, just writing this over, is equal to this portion here, y cos x 2x e to the y. So we get here y cos x plus 2x e to the y. And this means that we can integrate this to get f. And so so integrating with respect to x, of course, it's the integral of this expression with respect to x. So let me just write that out. It's going to be this partial derivative dx. And just doing that in one step here, if we're going to be integrating with respect to x, then the cos x here will change to a sin x, and this 2x will change to an x squared. And so the result is that we're just going to get y sine of x plus x squared e to the y. Okay, so that's using this part. But now we can use the other part, just as we did. Sorry, and I've made a mistake here. I should also add, of course, the arbitrary constant, which is an arbitrary function of y, g of y. Okay, so now that we've used this portion here, we need to use this portion here to solve for the gy. And let's do that. So solving for gy, we need to make the statement. So take df dy. This is equal to n. But let's differentiate this entire expression with respect to y and see what we get. We're going to get exactly just sine x plus x squared e to the y plus just g prime of y. Okay, good. But now this is equal to n. See, that's what this is saying up here. This is equal to n. So we just recall what is n. It's sine x plus x squared e to the y plus 2. And so we're just going to get sine x plus x squared e to the y plus 2. And this allows us to say that g prime of y is again just going to be equal to 2 now, because y, this here will cancel with this. Okay, good. And then we are allowed to integrate this function g of y with respect to the variable y, and choose the simplest function that satisfies this equation here. And I'm sure you'll see that this is just going to be g of y equal to 2y. And this allows us to say that, okay, let me just conclude with a bit more space. This allows us to say that f of x, y can be chosen to be just y sine x plus x squared e to the y, if I remember. Let's just check. Yes. It's going to be this plus g of y, and then we know we just have a lone 2y. So plus 2y. Okay? So the solution to the dE is just going to be given by taking this function here and setting it equal to a constant. Okay. And so that solves the differential equation, and we are done. Okay, so that's it for this video. We can also solve initial value problems involving exact equations, but we'll do that in the future. Okay, thank you.